Hey everyone, so we're looking at chord theorem today, and this is what it states. It says the angle between the tangent to the circle and the chord drawn from the same point of contact is equal to the angle subtended by the chord in the alternate segment. Now, some other books and some other people refer to this theorem not as the chord theorem, but the alternate segment theorem. So yes, that's another name for it. So this is how it goes. Say we have a circle with center O and point A on B, we draw a chord to B, then we draw another chord to C, then C and A are joined to form another chord again. So if we have G outside, we draw a tangent touching the circle at B to a point F. Okay, so now this theorem says we are required to prove that angle ABG and ACB, as highlighted over here, are equal. So this is the angle between the tangent and the chord. So this is the chord AB we are talking about. And chord AB subtends the angle over there at the circumference, ACB. And then the theorem says these two angles are supposed to be equal. Okay, let's see the proof. So proof. First thing we will do, we will construct a diameter BD and then draw AD. So then we'll see that we can first just make this statement that says OBG is 90 degrees. This is 90 degrees here because the radius is always perpendicular to the tangent at the point of contact. Then this means that this angle in here where the mouse is, ABD, is 90 minus our angle here. Okay, so you remember I was highlighting this with a blue color, so that's why I have it in blue there. Then we then see that this angle here is 90 degrees, BAD. So this angle here, 90 degrees, is the angle in the semicircle. Okay, then we take all the angles in this triangle and add them and say they're equals to 180. So we have BAD, we have this angle here, and we have this angle here. We have ADB and ABD. Okay. Now BAD we have as 90, and ABD we said was 90 minus ABG. So we can substitute them into the equation. So we have ABD as it is, and this one we have substituted for 90 minus ABG, and this one we said is 90. Now if we look carefully, you see that we have 90 plus 90, which is 180. Then we have another 180 on the other side, so they'll minus each other out. And this negative blue angle ABG will go to the other side and become positive. So we have ABD equaling ABG. So it means this angle now we have shown is equal to this one. Okay. Now, but we see that this ADB is in the same segment as this angle here. So they're subtended by the same chord AB, this angle and that angle. That makes them equal. So now, since this one was equal to this one, and now we've shown that this one is equal to this one, it means we can conclude that these two angles are equal since they're equal to the same thing. Since they're equal to the same thing. So that's the proof. Now I have done another proof for the same theorem to show that there's another way to prove this theorem. So I'll go on to the next proof. So it's still the same theorem. It's not a different theorem. So it's chord theorem, and it still states the same thing. The angle between the tangent to the circle and a chord drawn from the same point of contact is equal to the angle subtended by the chord in the alternate segment. So again, we still have our center O with circle O. Then our diagrams remains the same. A chord AB is drawn, chord BC is drawn, and AC is also drawn. We have our tangent JBF, and then we are required to prove the very same thing, that AGB is equal to ACB. So this time around, to prove them, we'll construct radii OA and OB. Okay. Then again, we start by saying OBG is 90 degrees, radius perpendicular to tangent. Now, it means this angle here again we can call 90 minus ABG. Okay. Then we see that we have an isosceles triangle here. It means this angle is the same as that angle. We can say BAO is also 90 minus ABG because we have radii OA and OB. They make this an isosceles triangle, and angles opposite equal sides are supposed to be equal. So it means both of these can be written as 90 minus this angle here. Okay, now we go into this triangle and say all the angles in this triangle, AOB, and these two angles here must give us 180. So we took those two angles to the other side. These are the two angles we just mentioned above here, ABO and BAO. So instead of these two, we're going to substitute these two things. Actually, the same thing for both of them. So we have 90 minus ABG and 90 minus ABG. So now what we have, again, we simplify here. The 90s will give us negative 180, and it will minus with this one. And then the negative will multiply the blue angles to be positive 2ABG. So here again, I showed that this 90s, they give us negative 180. They'll subtract each other out, and we're left with AOB equaling 2ABG. Okay, so now what have we done? We have proved that this angle is twice this one. But we remember that AOB again is equals to 2 times ACB up there. Angle at center is twice angle at the circumference. Then it means the two things are equal. 2ABG is the same as 2ACB. They're both equal to the same thing. Then if we divide both sides by 2 here, we get our final conclusion of ABG equaling ACB. Now I hope you enjoyed that. Let's flip over to the other side and see how we can show this theorem in our favorite program, GeoGebra. So here we go, we have our GeoGebra here, and the same diagram has been drawn. I just added two other chords just to show the other obtuse angle that is following the same rule. Okay, so again we can move this thing around, and we see that always these blue angles are equal no matter where we put A or no matter where we put C. When they change together. And even the red ones are the same. These is an angle between tangent and the chord BC, and BC subtends this angle E here. So these two are also equal. I hope you've enjoyed this. Like and subscribe, and please share the videos, write comments, with suggestions of what videos I should do next.